Why are you graduating? Yeah, I need a micro for next year. All right. So no homework for this week. The only thing you have is homework 4, which is due tomorrow. So we keep on the dates. So you have one extra day. I don't know if you noticed or not. I posted the solution by mistake, like for a few hours. I panicked because I have them posted, but I just I have a schedule that they come up, and then when I post the module, it posts everything. If I like, it asked me like, do you want to relog? Do you want to reinforce all of your data? And I forgot to say no. I said, yeah, I don't have anything in there. And then like 3 hours later, I'm like, hold on, what was that message for? And then it's like, okay, so if you've been checking Carmen for the last 4 hours, you have seen the solution. But I don't think anybody even checks the module, so that's great. Huh? Wednesday, tomorrow is Tuesday. Wednesday. Yeah, sorry. Yeah. I think today's Tuesday because I just want to go to the holidays. It is due on Wednesday, the homework 4. And yes, the solution is not anymore online. So okay, that it would have been very useless, right? Go through grading. Your homework, your PA3 is graded, but I need to check your feedback, your evaluation to adjust the gradings if needed. So I'll do that over the break. And for after the break, we don't have many classes left. Well, this is the last time I teach robotics. See, I shouldn't have recorded all of this. So I will look at what I had for like last year's and pick an interesting topic. Stuff that will come after the break won't show in your take home probably. It might show, I don't know, depending on which one do I choose. All right. So force control, I'm gonna just give you an idea of what force control is. We can't go too much into it, but for those of you that want to stay in robotic, you're in control, this will be a good introduction. You might have actually heard about it and know about it. So a lot of the industrial robot or a robot manipulator in their application, they are either in welding, painting, something that the pick and place, something that the robot interacts with its environment. All right. And you usually have a trajectory in this space. So let's say you want to paint an area or do a weld, you have to follow a path, right? So we have the path planning and path tracking. Last class, we talked about we can use set point tracking. If we can track every single point on that path or trajectory, then we are controlling that trajectory, right? Now that's when you don't have any interaction with your environment. Now imagine that you are writing something on the board, right? So let's say that I'm going to write Ohio, right? This is the path. Your robot to our manipulator should be able to follow this path. Now, this is your X and Y direction, right? Let's say this is X, Y direction. This one, all right? Your Z direction is the direction that this robot arm has to put pressure in order to stay in this path and don't fall, right? Doesn't fall. Does that make sense? So the trajectory, the task, the position control of this task within XY plane, if you're controlling the force, then the robot has to apply a force into this board, right? How much should it apply the force? Like what should be the force that is applying? That's something you need to control because it impacts here, for example, how thick or how thin or thick this lines are, or if you're painting, the quality of the thickness of the layer, if you're doing the weld, how thick or thin the weld itself is going to be. So it will impact something on your task, right? So that direction for these kind of robot is their force control, because how much force they're applying, while they have to control the position. So force control can happen at the same time of motion control. So you'll hear a lot of them, they call it hybrid motion force control. At some point, you just need to be able to hold something. That's just force control, right? For stationary. But most times, the robot has to maintain both of them. Now, we're going to look at force control separately, but most problem that you will encounter will be a combination of both motion and force control. We already solved the motion control problem, right? Equation of motion, dynamic. Now we have to define a force control and be able to put it in the equation of motion, so that we could use it as one big dynamic, so we can control it. Does that make sense? Now, our motion control was second order, right? A dynamic equation. We defined the second order dynamic equation. Now, for force control, there are different methods. I'm going to talk about impedance control, which we can model it as spring mass damper and becomes a second order differential equation. So you can easily combine it with your controller. But remember that this force control is the controller, is the external force that you'll put on the right side of your equation. The left side is the dynamic of your system. All right. That's basically it. So this is basically what I just talked about. So this is basically the strategy that while you are on the trajectory, you are sensing, you usually have a sensor that reads how much force you're applying. And based on that reading, you're controlling the force control, which is in Z direction, for example. And then you're following the trajectory in X and Y direction. So for force control, you need a kind of feedback. So you need sensory information here. There are different types of sensors for force or torque that you can use for sensing. You could have wrist sensor, for example. If there's a robot, you can have all degree of freedom, like the 3 degree of freedom on the wrist. You could have joint control sensor that using a gear reduction, you can see where it is. So you can see how much is rotated, how much based on that, you can calculate the torque. You could have tactile sensors that you can press and then read. How many of you used an application, used a sensor that measures force? What was it? What was it? Yeah, so how did you design it?
We put the bot on my platform, and then the little code reports.
Who else? Force control. I saw more than one.
We have typically like a load and rate sensor, which are unit-based for measuring spikes. So of course, you'll be able to understand the system based on checking.
So a lot of times, like, because force itself, you can convert it from measuring other things. So you can measure voltage and convert it, right? So in different application, you might have to measure something else and then convert it to using force in that application, right? So you could, what I mean is you could build your own force measurement sensor, all right? So now, if you want to apply that force control now, that's a feedback, right? You're going to bring it into our system. Now, how we go about, like, let's say the simplest way is to look at the block diagram. See, where does it show up in our system? Now, if I'm moving something, I'm controlling what? The position of that thing, right? So where should the force control appear? When am I controlling the force here? So you would use force as an input, let's say, to move your object, right, until you reach a desired position. Then you check the force if it's just need to be touching or it has to apply a certain force. So if you think about, you have a reference force, I have to apply 0.5 Newton on this to move it. And then you could have a kind of a PID controller, is usually PD controller. Then you will have a current position. I'm here, I need to get to a desired position and you find the error, so the comparison is the error. Then you have your environment, let's say the wall. So if I'm here and I need to reach to the wall, once I get to the wall, the more pressure applied, the more force the sensor senses, right? Without the position being changed. So I know I reached an obstacle, right? And that means that if I needed to stop or do or perform an action afterward, motion plan, then I can stop. Right? So basically your force control appears like this. If you're controlling the position using that force, it will appear before your position because you're using the control. Really depend on application though. Like if you're writing on a board, you're always in contact, but you have a fixed amount of pressure force that you have to apply. Then your sensor needs to read that pressure constantly. And if you are not applying that, it asks you to put more pressure until you reach there. So you could use that force control to stop something or to continue the motion, depending on what the job description is. Here is, so I'm going to go back to the previous slide. Here is the impedance control, how we model. So we are going to, which part of this is our dynamic, or system dynamic? What are the coefficients that represent the system dynamic? So MCG, right? So mass matrix, Coriolis forces, and gravity. Whatever shows up there is your system. How is all the other external forces if you have? It could be zero. Now, J transpose FE, that is our force control. So you could bring it on this side and keep it the external forces or this side. It doesn't matter. It's just a matter of sign which can appear inside. Right for that. Now, you'll see that here, that was the board, and you use that interaction, massive spring system. Now, how does this massive spring system, this is called impedance control, how does it represent our force control? Like, what characteristic of this system represent what we're trying to do? That's a question. Which one of them? Why massive spring system? What is specific about it that can help us to represent our force control? Yes. I can do it. So the displacement of what? The spring, right? So by adjusting the stiffness of the spring, you can control how much movement X is happening, and then you can find force from it, right? F is Kx, right? So if we needed to, for example, at some point of our trajectory, apply a force that control the force that stops something, to stop our motion, we can adjust this K to be large enough that would not allow any motion. Or if we needed to have a more flexible, so like there's more flexibility in the Z direction, then we can bring that K to be very small so we can move easily. So you could actually use this in adaptive control. So the best controller for robotics is adaptive control and robust control. So for adaptive control, as you are operating the system, you're checking the error and you try to reduce the error. That's a great way because you have the power of changing this case. And you also can change the damping, right? So that's why one way of designing a force control is impedance control, massive spring damper. And it gives you great flexibility to change that force control across your trajectory. Now, impedance control is used in many other applications. For example, if you are designing an assistive robot like ankle prosthesis, you have to define the stiffness, right? For someone to imitate humans gait. You can adjust that cage that will resemble human walking. So that's all force control, because when we step, at every step, there is a force coming from the ground, right? There should be a force from our body, from this, let's say, this was the robot, right? So in all the assistive robots, they use impedance control, just because of that, because in the interaction between force and environment needs to change depending on what the environment is. So let's say that you are following a path, like you're painting, you're welding, anything that you have to kind of move on a surface, impedance control becomes a very strong tool to do that. Now, I won't go into the details because right now we are in joint control space, right? So Q double dot, Q dot. To use the impedance control, you have to kind of move it to Cartesian and define your force there. And the conversion is a little bit outside of the scope of this class, but if someone was interested, all you need to do is impedance control, robot manipulator, and you have all the equations. All right, so I don't want to bore you with that because I'm not going to give you an assignment to do it, so I don't feel like giving you just the equation would be useful. But if some of you are interested, you can just easily find that. Now, your book uses a different force control, kind of force control. Same concept, they use range. So that's what the other slide is about. So we can assume that robot and environment interaction could be as, do you call that zeta? What is this? Psi, zeta? Zeta, okay. So it's V and omega, which is the linear and angular velocity of the end effector. We can define F to be our instantaneous force and momentum, F and N, and we can relate this to twist and wrench. Do you remember that when we defined twist, we talked about velocities, right? Angular velocities and linear velocities. Now, wrench is the force and momentum related to those twists, to those velocities. Then we can use the equation of motion and bring this F as the force control. If you are interested, your book has a very short section on it, and you can find 2 very short videos also from the authors that talk about it, but they also don't go very much into it because this is the topic of more advanced control, which is advanced robotic. I think if you take the 7,000 level of this class, you'll see a lot of this there. Because this is where you're interacting with the environment. This class is to know the robot itself, but usually the robot doesn't just work on its own, right? It's always interacting with something. If you're grabbing, how much force you have to apply? That's like very simple example. Are you going to squish this? At some point, you have to like hold. So you need to figure out what is the amount of force and hold it. So that is when you don't have motion, you just have force control. If the job is to erase or draw something, you have hybrid control. So you have force control plus motion control. Does that make sense? Okay. So these definitions are like, if you are looking at your book, I think they have twist and wrench. The 2 things that I want you to pay attention to is what is a natural constraint and what is an artificial constraint. Natural constraint is whatever comes from the environment, right? So the car is going, this is constraint, I can't push against the wall, I can't push against it. I'm not supposed to do it. I need to identify and stop, right? So that is natural constraint. Sometimes you need to, so the artificial constraint is the force that the system, the robot has been applied against the hand that needs to control it. So the robot is creating a constraint for something, for some motion, right? For example, to hold the razor, You need that the robot's force will be the artificial force because it's amount that is enough to hold that thing in place. Right, that becomes that is artificial constraint. So if you're reading the book and they talk about natural and artificial constraint, that's what it means, which I think is counterintuitive because you would think that artificial is something that you build and put in the environment, but it's backwards. So I think that is important to remember. So if you have, yeah. Any question about force control, like this really, really light touch, nothing, I didn't go into detail as much. Let's say I want to design can I design a PD controller for our force control? I can't, it's a massive spring system, right? Can you tell me how the equation would look like? So I can define an input, right? So I can say negative K X minus X desire, negative some KD X dot minus X dot desire, right? So it's the same thing. So if you're using the massive spring damper model, your PID control, well, it's not a PID controller, it's the same format as control law, but you're actually treating this as the difference in position and the difference in velocity of something, because if you're controlling the force, you actually have to control the velocity, right? So you have to stay at a constant velocity. And then you could also have zero acceleration. You can actually control the acceleration. Just you can say that x double dot desires must be zero. You can add it to your control law, but it resembles the PID. Because if you remember, drove the PID controller from massive spring damper model as well for robots. So impedance control will just look like this. And a lot of time you just see P. It's K times some X minus X driver. Because if you can control how far the object moves, then you can control the force by just some calculation. You don't have to actually control the position, but apply it because of the direction, right? So, yeah, that's about it. That's all I have for today. Did not go into detail because it will go above and beyond our. So, enjoy your break. I'll see you on Monday. Hopefully, all of you will be back by 8 p.m. on Monday. So